Dinosaur Fossil Diagenesis, a guide to interpreting host-rock interactions during burial. Diagenesis encompasses all of the chemical and physical transformations which a fossil is subjected to after the death of an organism. Changing temperatures and pressures from overlying sediments, as well as changing depositional environments, induce varying degrees of chemical and physical weathering. This alteration results in the dissolution and recrystallization of fossil fluids into interstitial pore spaces in the bones, and ionic exchanges between the organism's remains and the host rock where this burial occurs. To geochemically restabilize, terrestrial vertebrate fossils, such as dinosaur bones, begin to chemically homogenize with the surrounding soil solution. As they incorporate foreign mineral material into their crystal lattice, they achieve a new equilibrium in a permineralized state. Today, I will be discussing the various transformations that dinosaur remains undergo during and after burial. In continuing, I will address the kinds of minerals that are introduced into the bone structure during these processes and how biogenic signals recorded in these fossils provide insight into the behaviors of these massive organisms as they radiated through the Mesozoic. Unlike the tough, resistant calcite shells secreted by marine invertebrates, porous vertebrate hydroxyapatite bones are more susceptible to chemical and physical deterioration. As a result, exceptional preservation of these specimens is very rare and requires a specific depositional environment. After death, marine organisms are quickly buried in fine-grained muds or sands, which allow for a pristine preservation of their hard parts. As terrestrial animals, dinosaurs often did not inhabit environments that would have been conducive to their preservation. This is the reason for which dinosaur fossils are most observed in proximity to fluvial or lacustrine environments, close to a large body of water. Shortly after the animal's death, its remains are partly eaten by other dinosaurs. The area is flooded over and covered with fine muds and silts, which promote the skeletal preservation. During this first step of diagenesis, known as eodiagenesis, the specimen is quickly buried under moist conditions. The bone structure will begin to accept dissolved ions transported through the ground in local pore water. Characteristic groundwater soil ions such as trace metals, including iron, manganese, and strontium, rare earth elements, as well as chlorine and fluorine, are predicted to be enriched in the bone after burial, as these ions readily substitute for calcium and hydroxide in the crystal lattice. Furthermore, carbonate ions are often incorporated in the place of phosphate. These elements are therefore thought to be a good indicator of diagenesis, as they are not naturally synthesized in the bone tissue. It is also important to note that these transported ions are highly influenced by the local depositional environment. For example, Upper Jurassic dinosaur bones from the Morrison Formation of Utah show that it has higher concentrations of barium, nickel, lead, rubidium, uranium, vanadium, and yttrium compared to unaltered mammal bones. The authors infer that the higher concentrations of these trace elements, analyzed through a microprobe, are the result of groundwater enrichment in ions derived from alteration and dissolution of silicic volcanic ash. These enrichments can therefore be useful in extracting information about potential burial environments. Because of this vulnerability to alteration, this biomineral has been referred to by some paleontologists as nature's trash can. However, the flexibility of apatite in incorporating foreign ions plays a critical role in the subsequent diagenesis of bone and preservation over geologic time. Following this shallow burial, the dinosaur bones make their way deeper beneath the ground, where they are subjected to millions of years worth of sedimentation and deep burial. During this stage of diagenesis, known as mesodiagenesis, bones are subjected to fracturing and compaction as they are exposed to great pressures from overlying sediments, or what is referred to as lithostatic pressure. Meanwhile, the chemical structure of the fossil begins to destabilize under the intense temperatures and pressures that it is subjected to, as primary pore spaces begin to collapse. As a result, the hydroxyapatite will begin to dissolve and surrounding minerals penetrate and assume the original structure of the fossil. In fact, most of the fossils that we observe today are likely just a pseudomorph of their original material, and many have been completely permineralized. Over the course of millions of years, as permineralization occurs, the sedimentary column is uplifted and eroded continuously. The dinosaur remains that were once buried deep within the ground begin to make their way up to the surface, in a final stage of diagenetic alteration known as telodiagenesis. During this period, iron-bearing minerals that have been incorporated in the bone oxidize, and cements such as carbonate, siderite, and ferrodolomite are able to infill and cement fractures resulting from the deep burial. The formation of this iron oxide as crust around bone fragments or along fractures may also be a significant diagenetic feature. As reducing water is soaked into the sediment during the wet season, then evaporates during the dry season, a small volume of the water is retained in some areas of the bone structure. The water reacts with free iron ions incorporated in the crystal structure and in the sediment, and precipitates iron oxides around the bone fragments. This process therefore indicates seasonal variation during this stage of the diagenesis. The intense physical and chemical weathering mechanisms on these specimens leave paleontologists to infer a plethora of ecological data on structures that are, in reality, but a shadow of their former chemical composition. That being said, it is important to consider that many useful microstructures in the bones, such as Haversian canals, may still be preserved in morphology and are not completely lost to diagenetic alteration. However, the high degree of chemical change certainly begs the question: are there any useful biogenic signals remaining in these fossils? In other words, is it possible to detect any biological data from these permineralized specimens? Technological advancements over the course of the last few decades allow for the use of stable isotope compositions of biominerals such as hydroxyapatite to provide a record of dietary and environmental influences on a taxon. These isotope compositions can be used to study behaviors and to obtain paleoecological data on extinct species which would otherwise be unobtainable. Since only robust biominerals survive the processes of diagenesis and uplift and erosion, the isotope systems that can be applied to these specimens are very limited. Most stable isotope studies in vertebrate fossils focus on carbon and oxygen stable isotope ratios, although new studies suggest there may be other systems that can provide useful ecological data. The application of stable isotope systems consists of using the ratio between two stable variants of the same element existing in nature to infer diagenetic alteration or paleontological data by comparing this ratio to a global standard. For example, 16-oxygen is the most abundant form of natural oxygen, consisting of 8 neutrons and 8 protons, which add up to an atomic mass of 16 atomic mass units. Contrarily, another stable form of oxygen exists in the form of 18O, which has 2 extra neutrons than the former. As a result, this stable isotope of oxygen is heavier than the 16O stable isotope. During evaporation of seawater, the lighter 16O isotope is preferentially evaporated or fractionated into the gaseous phase. This leaves the residual seawater enriched in the 18O stable isotope. As these clouds move inland and begin to precipitate liquid water, the heavier 18O is preferentially fractionated and precipitated in the liquid phase. This depletes the remaining clouds of this isotope, leaving it more enriched in the lighter 16O compared to seawater the more inland that these clouds travel. Given that many of the early diagenetic interactions take place in conjunction with meteoric waters, the ratio of 18O to 16O in the hydroxyapatite crystal lattice may infer some significant paleoecological information. In a study concerning hadrosaurs conducted in Dinosaur Park, paleontologists observed how the isotope composition of hadrosaur bone recovered from marine sediments could not be distinguished from the isotopic composition of exclusively marine mosasaur bones. These values, however, differed greatly from the isotopic composition of hadrosaurs which were buried in a more terrestrial setting, where the 18O was significantly more enriched the closer the specimen is buried to a marine setting. This study demonstrates how oxygen isotopes can be used to infer depositional environments, and how these isotopic compositions can differ from one depositional environment to another. Other experiments have proposed that these isotopic ratios may be used to infer even more direct paleoecological data. In a study on the calcium isotope system, in dinosaur tooth enamel, which is more diagenetically stable than bone given the less porous structure, the authors were able to create a model whereby they could establish the percent intake of fish based on the enrichment or depletion in the heavier 44 calcium. Using this model, The authors inferred that the majority of non-spinosaurid theropods mainly fed on herbivorous dinosaurs, with less than 30% of their calcium being derived from fish sources. The giant crocodilomorph S. imperator likely exhibited a mixed diet, consisting of both fish and herbivorous dinosaurs, while the model supports a hypothesis by which spinosaurids may have actually been exclusively piscivorous. From an evolutionary perspective, the morphology of the dinosaur bones which are excavated from the fossil record provides very useful linkages between taxa and can be used to infer behaviors, locomotion, and feeding habits. However, it is significant that paleontologists consider the alteration that acts on dinosaur remains during burial and as it is uplifted and eroded from the sedimentary column. These geochemical processes can be very significant in determining paleoecological data. Though we still may be many years away from a Jurassic Park-like scenario where biogenic signals can be used to recreate one of these specimens, these methods will only achieve higher resolution with technological advancements. As we have access to more intricate mineralogical exchanges and a broader range of isotope systems, we grow closer to a scientifically accurate description of these magnificent creatures as they roamed the Earth for over 180 million years.